Good morning. We'll wait 5 more minutes for your colleagues to come and then we start. Good morning again. Tell me what questions do you have? What questions do you
Good morning. Would you like to solve for us an exercise in which we are supposed to use the Gram-Schmidt procedure?
have? Yes. Other questions do you have? Okay. So, of which means to use the procedure. Three families. We have two families of vectors, each of them having three vectors. We denote it by v1, v2, and v3, the vectors. And the first idea is to orthogonalize them. So starting with v1, v2, and v3, you must obtain another set w1, w2, w3, such that w1 and w2 in that product is 0. Then w1 and w3 in that product is 0. And w2 and w3 in that product is 0. It is called orthogonal family. And then you have to divide each vector by its length. and then you will obtain what is called auto norm. This is the idea. Okay, and now let's see what we should do. What should we do? How do we obtain such vectors which are perpendicular on each other? Well, we have to use these formulas. The projection of vector, say, A or vector is so W1 is 1, 2 minus 1. Okay, let's see. How do you compute this projection?
So will be dot product between 3, 1, 1, 1 and 1, 2 minus 1.
Yes.
Upper 1, 2 minus 1, 1, 2 minus 1. Again, that product. Multiply by the vector 3, 1, 1.
Multiplied by 2 minus
Oh, no.
1.
1, 2 minus 1.
And now the product is computed by multiplying the first element of this vector with the first element of this vector, and then adding them. And here again. We have 3 plus 2 minus 2, which is 4, 6. This is 2 over 3. And in the end, we get 7 over 3 minus 1 over 3 and 5 over 3. And this is W2. Okay, and now I will 5 minutes to find W3. So you have that V3 is 0, 1, 2. Okay, this is V3. And you have the formulas here, 5 minutes. Have you found W3?
Just a little bit to make the last computation.
Oh, okay, okay, I'm waiting. Have you finished?
Yes.
Just a second. Antonio, have you finished?
I need a little bit more time.
Okay, go give 3 more minutes. Have you finished?
Yes.
And you?
Could you please repeat?
Okay, Antonio left this meeting. Your colleague, you had a colleague. Oh, okay, Antonio, you're back. Antonio, have you finished? Antonio, can you hear me? We can continue. Okay, let's see the computation. Here is so computation step. Okay, what should you do in order to simplify your computations here in this area?
We can give a common factor 1 over 3 at the vector W2.
Yes, exactly. You need to with W2, which is perpendicular to W1. So you already have W1, which is this one, which is perpendicular on W2. But you don't like this vector because it has not so nice components. And this is why I'm going to work with a vector which will have integer components here. So if you divide W2 by something, or if you multiply W2 by something, then you will get a vector which will have the same direction as W2. So let's say that we draw smaller W2, this is 2. This is W2, this is 3W2. So this is our vector with 3W2. Okay, and if I multiply W2 by 3, I get 7 minus 1 and 5, which is this 3W2. But you see that it is also perpendicular to 1, so you don't need to work with such difficult expressions. When you can simplify them, do it. So in this case, W3 from here will be equal to 0, 1, 2, minus. Let's see how this projection looks like. So we have the difference between 0, 1, 1, 1, of dot product of 1, 2, so I'm going to projection onto this vector of this vector because we are going to work with this one. You have 0 plus 2.
The first projection will be 0 actually.
Yes, minus 2. This projection is 0. We have 0 over something times 1, 2, minus 1. So it is the null vector. Minus, and let's take a look. Let's take a look at this projection. This will be 0, 1, 2, 7, minus 1, 5. Minus null vector minus, you get 0, minus 1 plus 10 is 9. Over 49 plus 1 it's 50, plus 25 it's 75. You have 1 plus 9 over 75, so this is 84 over 75, and this is 2 minus this one, which is 150, minus this one, which is 105 over 75. But this vector is actually equivalent with
1 over 75, then the vector is minus 63, 84, and 105.
if let me write in this way that 3 equivalent with minus 63, 84, 105. But you can also divide by this vector. So you have minus 21, 28, and 35, right?
Yes.
And you can also divide this vector by 7. And you get minus 3, 4, and 5. So let's see what we have. We have that W1 is 1 to minus 1. 2 is this vector, which is equivalent to 7 minus 1, 5. And 23 is equivalent to minus 3, 4, 5. Let's check the dot product. So this is 7 minus 2 minus 5 is 0, is great. W1 with W3 now. This is minus 3 plus 8 minus 5 is 0. That's perfect. And W2 with W3. Minus 21 minus 4 plus 25. It's 0 again. So it means that all these conditions are fulfilled and we have these vectors. Now, from the beginning, you had to check if one of them are perpendicular. And if you take a look here, you will see that V3 is perpendicular on
V1.
on V1, because when you compute it here, W3, you place that projection on W3 on V3 on W1, so the projection of V3 onto V1 is 0. So it means that V3 is perpendicular on W1, which is V1. So you would have a more simplified process if you looked at first at V1 and V3. Or you have that V1 is 1, 2 minus 1. And V3 is equal to 2. So it means that the product V1 and V3 is 0 plus 2 minus 2, which is 0. So it means that they are already orthogonal vectors. So W1 can be seen as V1. W2 is V3. You know that W1 and W2 are perpendicular because V1 and V3 are perpendicular. And then you have to find W3 using V2. So this will be V2 minus the projection of V2 onto the first vector W1 minus the projection of V2 onto the second vector W2. And then you will have to make just this computation to find W3. Okay, so you will have this vector V1, W1, then this is W2, and this is from V2. And you have not so many computations as you had to do in the first case. Okay, so this is the second method. This is the second method based on the remark that V1 and V3 are perpendicular. But the general solution is this one that we have solved first. This is the general solution. Okay. have other questions? Okay, if you don't have other questions, let's find V1, U2, and U3. Okay, because we found W1, W2, and W3. We have an orthogonal family, but we must obtain three vectors which are perpendicular, and the length of each one is 1. Because what we have now is this. We have W1, which is this one, W2, and 3. We have three vectors perpendicular to y2, but the length of each vector is different from 1. And we want to obtain three vectors which have the length 1. So we want to obtain something like this. And that for the of U1 to be equal to 1, then U1 must be 1 over the norm of W1 times W1. Okay, W1 is this vector is 1, 2, minus 1. So the norm of W1, which is square root of W1 in that product with W1, is equal to
6.
yes, it's
Square root,
square root of
square root of 6.
square root of 6. Yes. So it means that U1 is 1 over square root of 6 times 1, 2, minus. This is U1. And if you don't trust me, compute U1 and see that this one is in a similar manner. U2 is defined in this way. W2. Let's use W from the first method, which is not this one, but this one, 7 minus 1, 5. It is square root of
65?
uh,
No, 75.
and see W3 is minus 3, 4, 5. Its norm is
49, which is 7.
Just a second, you have 9, okay, plus 16, which is 25, plus
Yes,
25,
yes, square root of 50.
which is square root of 50. So it means that u3 is 1 over square root of 50 times and C u. So then that u1, u3 is done. Or that. And did you understand?
Yes.
Okay. So you solve point B at home. Okay, point B is your homework for all of you.
Okay. Sorry, I didn't answer you earlier, but I had some troubles with the network. I don't know
It's
why.
fine. It's
Thank
fine. It's fine. Welcome. Okay. What questions do you have? What other questions do you have? What type of problem gives you difficulties in solving it? What type of problem? What would you like to know? What other questions do you have related to what you have seen in the seminars or course?
Can you make another example with linear differential equation systems?
Linear differential equation system?
Yeah, because we got the curse this, and if you can make another example with this,
But I think that I didn't hear so well. You have said that you have seen in the course the system of differential equations.
yes, it curse.
Okay, tell me what system of differential equations? I'm curious.
Could you please repeat?
What system? Give me examples. What have you seen in the course?
So we have the system. Okay, it's a simple one. This so
No, tell me.
y y1 prime equals 3y1 minus 2y2, y prime 2 equals minus 2y1 plus 3y2, y3 prime equals minus 7y3.
Oh, sorry. Can you repeat, please, for y prime is minus 2y1?
Yes,
Okay.
plus 3y2,
Okay.
and y3 prime equals minus 7y3.
And y o prime or minus 7y1, and that's all.
y3, not y1,
Ah, sorry.
and without prime, only y3.
Okay, but have you solved such a system in the linear algebra course?
Yes.
Yes.
Okay, nice. And what was the method used? With the exponential matrix or with eigenvalues and eigenvectors, and then you made the linear combination of such equations?
No, it was with eigenvectors and eigenvalues.
Okay, because the first methods are actually based on eigenvectors and eigenvalues, but the one with the fundamental matrix implies finding the matrix E at AX, where A is the matrix of the system. Okay, so you avoided this method.
Yes.
Let's see. Well, this system is prime, y2 prime, y3 prime equals, and then we have to write the 3 times 3 matrix, such that the matrix multiplied by y1, y2, y3 will give you these elements. So you have what matrix? You have what matrix?
A equals 3 minus 2, 0, minus 2, 3, 0, 0, 0, and minus 7.
And what should you do for this matrix A? First, we
The eigenvalues, then the
yes,
eigenvectors.
the values of A and the algebraic multiplicity of each eigenvalue denoted by A. So you have to solve that of A minus lambda I3 equals 0. This is the first step, right?
Yes.
How do you compute such a determinant?
We develop by the last column or last row. Doesn't
Yes,
matter.
yes, exactly. So you have minus 7 minus lambda times minus 1 at the power.
3 plus 3.
Yes, because this is on line 3, column 3, times this determinant equals 0. And let's write it this way. Let's put this 3 minus lambda minus 2 times 3 minus lambda plus 2. Okay, because 4 is squared, and you have a squared minus b squared. Okay. And now let me write directly the solutions. And now you have that lambda 1 is minus 7. Lambda is one, and lambda 3 is 5. What is the multiplicity of lambda 1?
1.
Yes, because minus 7 is just one solution for this equation. If this expression was the power 2, it would mean that lambda equals minus 7 is twice solution for this equation. So the algebraic multiplicity is 2, but the algebraic multiplicity is 1, also for lambda 2 and lambda 3. So let's write that lambda 1 is minus 7, and that the algebraic multiplicity of lambda 1 is 1. And the same for numbers. What should you do next? You should find that. You should find the
Eigenvalues.
eigen
Vectors.
vectors.
Oh yes, eigenvector, sorry.
It's fine. So you have to find the vector and the geometry multiplicity of which eigenvalue, and this geometry multiplicity, sorry, is denoted by mg. mmg. For lambda 1, which is minus 7, you have that a minus lambda 1 I3 times a vector v is the null vector. So you have that. If you subtract from here minus 7, then you will add a 7 to it on the main diagonal. So you have 10 and 10 here, and here 0. Okay, so you have 10 and 10 and 0, and then the rest of the elements will be copied. A vector v from R is vector AC, and 6 is 0, 0, 0. So you have that 10 minus 2b is 0 minus 2a plus 10b is 0, and 0 equals 0. Okay, I will give you 2 minutes to solve this system if you don't have the solution already. You have the solution, right?
Yes.
Okay, so from this system, you have that A and B are?
Just a second. 0, 0.
Yes. Because if you multiply the second equation by 5 and you add, you get that A 0 and B 0. Okay, what do you see?
C is a real number.
Yes. C could have any real solution. So the eigenspace for the eigenvalue lambda 1 is the space of all the vectors. Let me write them on lines. You have vectors 0, 0. C, right? Because C is real. C could take any possible value. Let me write in this way, transposed. Where is R? So this space is C times 0, 0, 1 transpose with C in R. And if you denote by 1 this vector, then you will have that V1 is a basis of S lambda 1. So the dimension S lambda 1 is 1, and this will be the geometry multiplicity of lambda 1, because the geometry multiplicity of lambda 1 is defined as the dimension of this space. Okay, so mg is 1. And you have that m is also 1, so it's fine. When they are equal, it means that you will have a diagonal form, so it's great. Okay, I suppose that you already have the computations for lambda 2 and lambda 3, right?
Yes.
Yes.
So let's see briefly what we should do for lambda 2, which is 1. You will have to solve the equation A minus lambda 2I times the vector C equals 0, 0, 0. So you have A, C.
So we have B 0.
Which is 3 times 0. This is B2, let's say. And geometry multiplicity of lambda 2 is?
1.
Yes, is also 1. B minus B or A and minus A?
The last one is B minus B 0.
Oh, and now we have to write. So we write. So the pen is going. So, so we write the fundamental mental system of solutions. Give you some explanations here because I suppose this is the part that you didn't understand well.
Yes.
Yes.
The idea is the following. Here, this system, this one, is a homogeneous system. Why is this system homogeneous? Because you don't have here something which is a constant or a function depending on t. Okay, let's say that in all the cases, the functions depend on a variable t. So let's say that y1 is a function y1 depending on t, then y2 is a function depending on t, and y3 also a function depending on t. So you have three functions, three values that depend on t. And you don't know that, so you must find that. This system could also have here plus t, plus e at t, don't write, just listen, and plus 2. In this case, you will have a system which is not homogeneous because you would have other functions added here at the end of each equation. Your system is homogeneous, and this is a great advantage because if this system is homogeneous, then the set of all the solutions of this system is a vector space. So let me write here that the system at the Okay, let's go back in high school in 11th grade. If you have a homogeneous system of equations, let's say that 3x plus 2y is 0 and 9x minus 7y is 0. This homogeneous system with a solution per word on the matrix, right?
Yes.
Okay, let's say that we have a system which has more than one solution. So let me change here. Let me put 6 and 4. In this case, your homogeneous system has an infinity number of solutions. So the solution for this system will be 1 by minus 2y over 3, right?
Yes.
With y I, it's the set of the solutions. Is the set of vector space?
Yes.
Yes, it's y is minus 2 over 3 and 1, right?
Yes.
So this set of the solutions of a homogeneous and linear system is a vector space. So in order to write the solutions of this space, I need a basis. And in this case, the basis is given by the vector minus 2 over 3 and 1, correct?
Correct.
Okay, so let's go back to our system. Well, we have a system which is homogeneous, and we know that the space of solutions is a vector space, similarly with the system that you have seen earlier. Well, what do you need to find in order to be able to write all the solutions? What do you need to find?
A basis.
Yes, exactly. So you need a basis. And this is why we must find some functions which are called fundamental functions. So we need to find a basis for the space of solutions. And this basis consists of what do you have in this basis? What kind of vectors do you have? Vectors in R2, R3, matrices, functions.
In the basis, we will have vectors from R3.
Just a second. The solutions of the initial system are actually
Functions.
functions, exactly. So the solutions are functions. I have a system in which you know some functions. So I have to find a basis for it with functions. Okay, this basis consists of functions which are fundamental. So let's see how this function looks like. And let's take for lambda one, you have that area of lambda one is 1 and g of lambda 1 is 1. So you have that MA is equal to mg. So in this case, you have a function denoted by y1. Let's say y1 with a bar on it. y1 bar, which is given by e at lambda 1 t times an independent eigenvector, which is v1. So these functions are denoted here by y1 bar, y2 bar, y3 bar, let's say. And this y1 is actually a function which depends on t. And y1 on t will be e at lambda 1 is minus 7. Minus 7 times a vector, which is a vector corresponding to lambda 1. We have found that the eigenvector corresponding to lambda 1 is 0, 0, 1, right? So this is 0, 0, 1. And this is 0, 0, e at minus 70. Then, for you have that of 2 is mg of 2, which is 1. So the corresponding function will be given by, and now you tell.
It's e at power t.
Okay, let me write it this way. Times
1, 1, 0.
Okay. So you take bar of t, 2 bar of t, or 3 bar of t, which is a basis in space of solutions of the initial system. So how a solution will look like?
Will be like a column from a matrix. If you give values to t, we get like, I don't know, let's say from the first one we get 0, 0, e at power minus 14, let's say.
You don't have to give value because t is the variable.
Yeah, but the t you put values to it to get
No,
solutions.
no,
No?
no. The idea is the following. If you have a basis, how do you write a
No.
general solution? As a
Linear combination?
Yes,
No.
yes. So, if y of t is a solution of the system, then y of t will be a linear combination of those functions, which will be a constant times y1 bar of t plus another constant times y2 bar of t plus another constant times y3 bar of t. And C1, C2, C3 are in. But y of t, I mean y1 of t, y2 of t, y3 of t. Okay, so it means that y1 of t, y2 of t, y3 of t is c1 is 0 e at minus t plus c times y2 is e at t is t and 0 plus c3 which is e at 5t with a minus e at 5t and 0. Right?
Yes.
So this is a solution because a solution is the vector which contains these three unknowns of the system, okay? So a solution is a vector consisting of these functions. This is y of t, and this is y prime of t. Okay, so y of t, the solution consists of y1, y2, y3, which are functions. And the solution is a linear combination of the elements of the basis. So the solution is you have here 0 plus C2 e at t minus this one. Then you have 0 plus C2 e at t plus C3 e at 5t and C1 e at minus 7t. Or not?
Yes.
So T is you have an infinity number of solutions here. Then we have questions related to this solution.
What if you get MA different from MJ? Then we will get like the system cannot be solved, or we have
No,
other things to do. Oh, okay.
you can solve the system. A very good question. You can solve the system, but you have to find what is called a principal vector.
Oh, okay.
So if you don't have J equals MA, it means that the matrix A from the beginning doesn't admit a diagonal form,
Yes.
but it admits an almost diagonal form because all the eigenvalues are in R. And
Yes.
this almost diagonal form is the Jordan form. And in order to find the Jordan form, you have to find principal vectors. So let's say that MA is 2 and MJ is 1. Then you have to find 2 minus 1 principal vector. So 1 principal vector. And then you will have functions y1 bar and y bar depending on the eigenvector and the principal vector that you have found. So this is why I have talked to you at the seminar about principal vectors. Professor Pita didn't have the time of the course to tell you
Yes.
about principal vectors, and she told me to tell you a few words if I have time at the seminar, and have found some time to talk about principal vectors. But of course, have so much subjects to talk about that you have the time. And I have talked to you about principal vectors because I knew that in the second year of study you use them a lot. Professor Pita made a very interesting application with you. She has chosen to solve such a system in order to show you what eigenvalues and eigenvectors are used for. And they have applications in solving such systems. So it's very nice that she found the time to show you an application of eigenvalues and eigenvectors. But of course that she hadn't had the necessary time to explain to you that theory, because there are a lot of things to be explained here. Uh, because in the second year of study at special mathematics, you will see the theory for solving such a system. So in the second year at special mathematics, you will see the entire theory and also the case when MJ is not equal to MA.
Okay.
This is the idea of this topic. Then if you have other questions or what other questions you have.
Can a bilinear form cannot admit a canonical form?
No,
It's not possible.
quadratic form always admits a canonical form, because the matrix of a quadratic form is a symmetric matrix. And you have a theorem which tells you that every symmetric matrix has real eigenvalues, and more than that, the multiplicity of each one is equal to the geometric multiplicity of each one. So if you have a symmetric matrix, then it admits a diagonal form. And the fact that the matrix admits a diagonal form is equivalent with the fact that the quadratic form admits a canonical form.
Okay, thank you.
Okay, so welcome. So you will always have a canonical form for a quadratic form because the matrix is symmetric. What questions do you have?
Okay, but if he admits a canonical form, it can be 0.
If canonical form is 0, it means that the previous canonical form, the previous quadratic form is 0.
Okay, so it's only in the case if the quadratic form is 0.
Yes. The diagonal, the canonical form is 0 if and only if the quadratic form is 0.
Okay.
Or it may be, or it will have elements. So let's see what happens if you have such a matrix. Let's say that you have 0, 0, 1, 0, 1. Let's say 0, 0, 0, and 0. Let's say that you have a matrix A, which is the matrix assigned to Q with respect to the base. Could you have the canonical form equal to 0? Could you have the canonical form equal to 0 or not?
I think yes, because we'll get the one eigenvalues will be 0, let's say.
Yes.
And I think that's all.
Okay.
No.
But if you have the eigenvalues equal to 0, you will have just zeros there. And actually, your Q of X will look in which way?
X1, X3?
Yes,
Two
actually,
X1, X3. Two.
2x1, x3. Okay, but in this case, you will have that m, let me write in this way. You will have that lambda equals 0 is an eigen value, okay, with ma of lambda equals
1.
ma, the algebraic multiplicity of. Is it an eigenvalue or not? Did we make the wrong computations? Let's see. Let's take a look at A minus lambda I3. Let's take a look at the determinant of this matrix. So you have minus lambda 0, 1, 0, minus lambda 0, 1, 0, minus lambda, right?
Yes.
And you will have minus lambda squared from here, plus 0 plus 0 minus plus lambda, right?
Yes.
Okay, plus 0 plus 0. So actually, you won't have the eigenvalue lambda equals 0 because you have here 1 and 1, 1 and 1. This element won't be 0. The determinant is just minus lambda squared. The determinant is minus lambda squared plus lambda because of this secondary diagonal. So you don't have all the eigenvalues equal to 0. Do you see?
Yes.
So you have lambda minus lambda squared. So you lambda times 1 minus lambda times 1 plus lambda. So the actual form of A is 0, 1, and minus 1. So the canonical form of Q will be
Uh, 1 x2 at power 2 and minus 1
Ex-
x3 at power 2.
exactly. So it's not 0 for x prime x3, right? So can this quadratic form be equal to 0 for each x2 prime, x3 prime? No.
No, it's only
So
one case
you
where it is 0.
yes, so you won't have that the diagonal form of the 0. So you won't have that the canonical form of Q is 0. But what happens if you have here 1 and 1 instead of this one? So let's take another example. What happens now? Let's say that the matrix of Q with respect to canonical basis is okay. So it means that Q of X is
X 2x 2x1.
developing after the line 3 or 3, you get minus lambda times this determinant, which is again lambda squared minus 1. So you'll have again three solutions. Okay, so canonical form of Q won't be 0. So the canonical form of Q is 0 if and only if you have this matrix A 0, so Q must be 0. Okay, did you get the idea?
Yes.
Okay, that's perfect. But this was a very, very good question. Okay, me, what questions do you have? What questions do you have? Do you have something that you didn't understand so well in the course or in the seminar?
No, I don't think so. Maybe uh, could you give us some examples with of exercises that we are supposed to have at the test?
Um, we discussed with Professor Pita about the test. So we didn't establish how the test look like. So I don't know to give you examples, to give you models of tests, but all the problems that you have seen in the seminar could appear at the test, and also all the problems that you have seen at the course could appear at the test.
Okay,
Okay, so I don't have a model, but all the problems worked can be a possible subject for the test.
okay.
And I have seen 10 minutes ago when I talked to Jenna that you don't mind. Do you have questions about something from the course or seminar? Maybe you don't hear. So I understand that now how to solve all the problems. So all of you know to solve all the problems in the seminar, right?
For me, I finished all my questions for this year. I need to wait for the next year.
Okay, so you have some questions for the following year, but you don't want to tell me now all the questions, right?
It's like a present.
Okay, okay. Do you know how to work with scalar product or dot product, cross product, mixed product?
Actually, how we make a dot product between two functions?
A dot product? Well, it depends. It depends. Usually a dot product between two functions which are continuous is defined as the integral. So let's say that you have two functions f defined a b with values r and defined on a b with values in r. Functions which are continuous. The product of f and g could be defined as the integral from a to b from f of x times g of x dx. Okay, this is an example of a dot product function. And if you do not trust me, you could check the properties of a dot product. So you will see that if instead of f, you will have an a times f1 plus b times f2, then you will obtain here a sum of two integrals with the constants in front of them. So you will have a linear combination of dot products in the first argument. Then a real expression here because the final result is an expression R, and the final result is something R. So I would write it this way. This is R only. It means that this product is symmetric. So FG in that product is GF in that product. Also, dot product with f and f, you will see that it will be integral from f times f, which is f squared. F squared is positive because f has real values, so this expression will also be positive. This real number will also be positive. And this one is zero, because f is a continuous function, it means f squared is zero, so f is zero. So you have all the conditions satisfied. So this is a dot or an inner product or a scalar product. And depending on the functions, you have to compute this integral. Okay, let's say that, let me give you an example. Let's say that f of x is x minus 1 and x is sine of x. And so let's say that f and g are defined on 0 by values. Then in this case, the dot product between f and g is the integral from 0 to pi from x minus 1 times sine of 2x dx. And now I will give you 5 minutes to find the value of this dot product, and then you tell me. Have you found the solution?
Yes.
Let's see.
The result or the integral?
Can you repeat, please?
I say the integral or the result is numerical result.
Oh, no, the result of the integral.
Could you please repeat?
The numerical result.
It's
Result.
minus p over 2. I
Oh,
guess.
let's see how you get that result.
So
So this, okay. What have you done here?
we can keep like this. I want to say we can keep like this, or we can multiply by sin or 2x and then use the formula for this to compute, and that's it.
Just a second. How do you multiply by sinus here?
We put like x sine 2x minus sine of 2x, and then you
Okay,
have
and
integrals.
okay, and the first one to be computed in which manner?
You'll use the, I forgot the name right now, but it is a formula.
Integration by parts?
Yes, by
Integration by
parts.
parts. Yes, I
Yes,
forgot
so
the name.
okay, it's fine, it's fine. Let's use the integration by parts directly. So this is actually integral from 0 to pi from x minus 1 times, and this is actually minus cosine of 2x over 2, the derivative of this function, right?
Yes,
Okay. So this is sine of 2x, but I'm going to write in this way. And this is x minus 1 times minus cosine of 2x over 2 from 0 to pi minus integral from 0 to pi from the derivative of x minus 1 times minus cosine of 2x over 2. Cosine of 2 pi is cosine of pi.
zero.
Is cosine of 0,
Yes.
which is 1.
Oh,
This is 1. This is plus times integral of cosine, which is sine. Okay, so this is minus 1 over 2 times pi minus 1 plus 1 plus 1 times sine 2 pi. And this is zero, okay? So it's minus 1 over 2. Okay, do you have other questions? Then if you don't have other questions, please allow me to.
Can you please explain the part where we did the integration, like the second step? I don't really understand.
This one.
Yes.
Okay, this is the formula that we have used. This is the integration by parts. You have this product. You know that this is x minus 1. H prime will be sine of 2x. But because h prime is this one, then h will be this one. And we have here x minus 1 times minus cosine, which is this term, from 0 to pi, minus the integral from f prime, which is x minus 1 prime, times h, which is this function which comes here. Okay, and now you have to compute the values in 0 and pi.
Thanks.
Welcome. Okay, let me download the attendance list. That's all I talked to now, so I present. Also, I talked to Antonio, and I know that he's here. And with Jenan Omer, I have talked a lot. And Popescu Emanuel, do you hear me? Maybe, but you earlier didn't respond, so I suppose that your microphone is not working. Okay, I see that you're here. Have a nice holiday and nice week too. Goodbye.
Goodbye. Have a nice holiday.
Goodbye.
Goodbye. Have a nice holiday.
Merry Christmas.
You too.
You too.